Assalamu alaikum wa rahmatullah. Good day, everyone. In this video, we will solve a problem on superposition of magnetic field. Problem 1 says you have two long straight wires. This is wire 1 and this is wire 2. They are long and they are also straight. Lie parallel to each other. We can see they lie parallel to each other as shown in the figure below. This is the figure. They each carry a current of 6.0 amperes, meaning where one carries a current, this current passes through it and the magnitude of the current is 6.0 amperes, where 2 also carries electric current of the same magnitude 6.0 amperes, but in opposite directions. As you can see, this one carries the current to the left and this one to the right. What is the magnitude? What is the magnetic field at P, point P? Here is point P. Point P is 8.0 centimeters from wire 1 and wire 1 is 8.0 centimeters from wire 2. This means point P is 8 centimeters plus 8 centimeters, which is 16 centimeters away from wire 2. And then we are given the permittivity mu naught as 1.26 times 10 to the power of minus 6 Tesla meter per ampere. So the question is, what is the magnetic field at point P? We know that since wire 1 carries current, there will be magnetic field due to wire 1 at P. Wire 2 also carries electric current, so there will be magnetic field around this wire 2 and its field extended to P as well. So at point P, you have magnetic field due to wire 1, you also have magnetic field due to wire 2 combined together. So the question is, what will be the resultant magnetic field due to both wire 1 and wire 2 at point P? Okay, this is just an introduction to understand the nature of the problem. Now, to solve the problem, we need to draw a diagram. Okay, I'm going to start with wire 1. Okay, I'm going to start with wire 1. Let's say this is where we have our point. This is where we have our point P. Point P being here. This is my point P. Now, where 1 is 8.0 centimeters from point P. 8.0 centimeters, you divide it by 100 to change it to meter, and you will get it in 0.08 meter. So where 1, let's say where 1 is somewhere here. Now, we have to use the right-hand rule to determine whether the magnetic field is into page or out of page at wire 1. Okay, this is the direction of the magnetic field here. According to the right hand rule, we take our thumb here and align it in the direction of the current, and then we curl our fingers. You see, so if I put, this is my thumb, is pointing in the direction of the current, and then if I curl my forefingers, you see it will be touching the page. So we see that it is into page. Okay, the magnetic field for wire 1 here is into page. So when we are drawing, we know that we have the symbol for into page, which is a cross here and then encircled. Okay, this is where we have wire 1. Okay, and the field is into page. Its distance from wire P 0.080 in meters. Then down here we also have wire 2. So I'm bringing the diagram again. Look at wire 2 here. Now if I align my again my thumb using my right hand, my thumb is in the direction of the current for wire 2. Okay, and then I curl my finger, you see it is pointing out of page. My forefingers are pointing out of page. You see that? So for out of page, we know the symbol should just be a dot. Okay, a dot here, circle here. It means the magnetic field at this point is out of page and this one into page. So we have wire 2 here. Now we have to draw a Cartesian plane here. Okay, to make it easier, we draw a Cartesian plane. Okay, this is the y plane, and then wow, so this is the x plane. Again, the distance from here to here we know is 0.080 in meters. Okay, so moving on, how do we draw magnetic field due to wire 1 at point P? Okay, if it is into page, we know that the field here is around the wire and it is considered the direction is clockwise. Look at it here. You put your thumb into page like this. This is my thumb at wire 1. Then I curl my finger. If I curl my finger in this direction, you see it's clockwise. It's clockwise. So this means I will have concentric circles here, okay, for the magnetic field. Okay, and they all point in clockwise direction. These circles continue until you have another one that passes through this point P. Okay, and its direction is also clockwise. You see that? So at point P, the direction of magnetic field at point P should be the tangent, the direction of the tangent at P. So the tangent at P, we draw the tangent at P. Since it is in this direction, clockwise, we draw the tangent in this direction to the right. So this is our magnetic field at P due to wire 1, and we call it B1 vector. Okay, B1 vector, and its distance from wire 1, you see this is 0.08, so it's 0.080 meters. So we draw it like this. This is its distance from wire 1, and we are going to call this distance our R1. So R1 is equal to this one. Now for wire 2, if you want to draw the magnetic field here, remember this is out of page. If it is out of page, to draw the circles representing the magnetic field and also to understand the direction, you take your thumb to point outward. You see, point upward, it means out of page, and then you curl your finger in this direction, and you can see this direction is counterclockwise. You see, so it means you have another first of all, you have circles here. Okay, first of all, you have circles here, you see, that are pointing counterclockwise. Their direction is counterclockwise and is the direction of the magnetic field, because the magnetic field is out of page here. So it means you have one that passes through here. You have one, of course, that comes all the way and then passes through point P in this direction. You see that? In this direction. So its direction should be here. The direction of the magnetic field due to wire 2 at point P, since it is counterclockwise, should be drawn to the left. It should clearly be drawn to the left. See that? And we are going to call this one B1, meaning B2 vector, meaning the direction of the magnetic field due to wire 2. Now we have to draw its distance. Its distance from the distance of point P from wire 2. We have to add these two distances and it will give us 0.160 meters. So this is 0.160 meters, and we will call this our R2. See? So see, great. Now we have the diagram. The next thing we are going to do is that we will calculate the magnitude of B1. We will also calculate the magnitude of B2 and get their vector sum. That will give us the resultant magnetic field at P. So we know that the magnitude of a magnetic field, since they are the field is generated by wires, the formula we use is mu naught I for current divided by 2 pi r. You see that? So if we apply this formula to B1, we will say that, well, our B1 is equal to mu naught I divided by 2 pi r1. Everything the same because we know that the current, we were told that they carry the same current, so they only differ in R1. Okay. Here from the problem we can see that the current is 6.0 ampere. So we move on and say this is equal to, okay, we start with mu naught. We are given the value of the mu naught in bracket. Mu naught equals 1.26 times 10 to the power of negative 6 in Tesla meter per ampere. So we open bracket and say 1.26 times 10 to the power of negative 6 Tesla meter per ampere. And then next, our current from the problem, the current is 6.0 ampere divided by 2 pi. 2 pi is a constant. And then our R1, where is R1? Look at R1 here, is 0.080 in meters. 0.080 in meters. This is equal to, clearly we see that per ampere will cancel the ampere here, and the meter cancels meter, so we will get our magnetic field in Tesla, which is the SI unit of magnetic field. Okay, now we bring our calculator. When we bring our calculator, we start with the denominator. Okay, the denominator is 2 pi. Let's open it. 2 shift pi. You see, the pi is here, so you press shift before you press exponential, and then you have the pi there. 2 pi then multiplied by 0.080. Then this will be our answer. The answer is given in terms of pi. If you want it in decimal, press this function SD. So I press here, I have it in decimal. Next, since I started with the denominator, I will now press the reciprocal function, this very one. So I press this one, and then I will now say times everything I have in the numerator, 1.26 exponential negative 6 multiplied by 6.0. Then I will have my answer as 1.504 times 10 raised to the power of correct to 3 decimal places times 10 to the power of negative 5 in Tesla. This is my B1. So I move on to get my B2. Using the same formula, of course. So my B2 is equal to mu naught I divided by 2 pi R2. They only differ in value of R. Every other thing is the same. So we continue and say, okay, our mu naught is 1.26 times 10 to the power of negative 6 Tesla meter per ampere. Then open bracket again, 6.0 ampere close bracket divided by we have 2 pi here open bracket our R2. Okay, we go back to the diagram. You see your R2 is 0.160 in meters, so you write that 0.160 in meters, and again the meter you have here cancels the meter, per ampere is cancelled by ampere, and you will have the unit in Tesla, which is the unit of magnetic field. So again we bring our calculator, and as usual we start from the denominator. 2 shift pi multiplied by 0.160, it will give us in terms of pi, and as a fraction I press the ST, I have it like this. Then I will now multiply by the numerator 1.26 exponential negative 6 multiplied by 6. So I have my answer as 7.600 times 10 raised to the power of negative 6 in ampere, oh sorry, in Tesla. This is magnetic field. Now let me bring the diagram again to get the resultant. We know that this one, the two magnetic fields are horizontal, okay, and since they are horizontal, we say that they are parallel to the x-plane. So we consider this one as positive and this one as negative. This is in the positive x direction, this is in the negative x direction. So we combine them by saying, okay, total magnetic field at point P is given by, okay, so I will call this one B as the total magnetic field at point P, okay, and this will now be let me say field vector here, and this will now be a magnitude of B1, okay, and then of course we know this one is along the x-axis, and the unit vector along the x-axis is I, so I will put I vector, okay, plus then the magnitude of the second one B, B2. B2 is also along the x-axis, so the unit vector along the x-axis is I hat. Okay, now I'll continue and say, okay, this is equal to my B1 is positive, is in the positive x-axis, and its magnitude, I got its magnitude, look at its magnitude here, okay, 1.504 times 10 raised to the power of negative 5 in Tesla. Okay, this is what I have, I vector, then plus, then I open bracket again, but my B2, since it is directed in the negative x direction, it has to be negative. This is important, even though in the calculation you didn't see a negative sign here. You consider the direction. The negative sign comes from the fact that it is directed in the negative x direction, so it has to be negative because it is a vector, not a scalar quantity. So we give it a negative sign and say negative 7.600 times 10 raised to the power of negative 6, also in Tesla. Then its direction is also I hat along the x direction. So plus this will be equal to, we know that plus minus will be minus, so at the end you will be saying this minus what you have here. So we press again and say 1, we are going to say 1.504 exponential negative 5 minus, then we have since I press minus, I don't have to press this one now, so 7.600, okay, exponential negative 6, okay, so press equality sign and your answer will be 7.44 times 10 to the power of negative 6 in Tesla, all of them along this along x axis. Okay, they are positive. Okay, it means that the resultant field is the resultant field, since it is positive, the total of this and this is in the direction of B1, meaning this B that you have is directed here, is directed along here. It has the same direction as B1, this total vector. This is the sum of this and this, okay, and it is in the same direction as B1. And we see that this B1 is into page, okay. Remember when we were getting B1 is due to wire 1. So you see this direction here, we put our thumb in the direction of the current, and then we bend our finger, we curl our finger. You see it's into page. So since the total field is also in the same direction as B1, okay, we say that it is also into page. So because it is a vector, we have to give both the magnitude and the direction. So here we will just put comma. This is the magnitude of B1, and then the direction is into page. This way you have the magnitude here. This is the magnitude, okay, its size, its amount, and into page tells you the direction. So you have completely specified your magnetic field. I hope it's clear to all of you. Thank you for watching. Assalamu alaikum wa rahmatullah.